Hello everyone. This is the second lecture in Computer Science Crash Course. In this lecture, we are going to learn about how numbers play an important role in processing and representing information in computing. This lecture and the next lecture will be related to information layer of the computing system. All information in computers is stored and processed in form of digits 0 and 1. Hence, it is called digital information. Memory location in computer has either 0 voltage or low voltage or high voltage. Low voltage is represented with 0 and high with 1. Hence, all types of data or information can be represented with binary numbers or combinations of 0 and 1. To represent textual data in binary, different coding systems have been developed. Different methods of representing graphics, video, and audio data also exist. To understand this layer, first we will learn about number system. Next, we will learn about how information is digitally represented in computers. A number is a unit of an abstract mathematical system subject to the laws of arithmetic. That is, you can do different types of calculations and perform operations on numbers in mathematics. Numbers came before writing, used to count, measure, and label objects. Based on different properties, numbers have been categorized into the different sets in mathematics. These categories are natural numbers, whole numbers, integers, rationals, irrational, real, and complex numbers. Focus of this lecture will be whole numbers, that is, positive integers. They are used for counting. Counting is keeping track of quantity of individual objects. Counting happens by successive addition of a specific value in the current value. Arithmetic operations like addition, subtraction, multiplication, and division also use whole numbers. And whole numbers are also used for labeling for identification purposes. Number system is a system for writing or representing numbers. Two things are important for a number system to function: symbol or figures. Every number system has a specific set of figures which are used to represent a number. For example, figures for decimal number system are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Base. Second thing is base. Base represents total number of figures in a number system. For example, number of figures in decimal is 10, so the base is 10. Figures in binary are 0 and 1, so the base of binary is 2 because there are only two figures in binary. In positional notation of numbers, digits in a number are assigned place values according to the position. Place value for digits are actually determined by power of base. The number is equal to the sum of products of each digit by its place value. In a decimal number from right, place values are units, tens, hundreds, and thousands, etc. So number 729 has 7 as 100, 2 as tens, and 9 as units. With respect to base in decimal, unit is 10 power 0, 10 is 10 power 1, and 100 is 10 power 2, 1000 is 10 power 3, etc. 729 can be expanded into 7 multiplied by 10 square plus 2 multiplied by 10 power 1 plus 9 multiplied by 10 power 0. Number in positional notation is like a polynomial. In polynomial, there are terms joined by plus and minus. Term with highest exponent is written at leftmost and lowest at rightmost. Here n can represent number of digits in a number, r is the base of number system, and d is the digit at nth position. Here we represent 7341 in polynomial form. Here n is equal to 4 number of digits and base is 10 because it's a decimal number. So 7341 can be written as 7 multiplied by 10 power 3 plus 3 multiplied by 10 power 2 plus 4 multiplied by 10 power 1 and plus 1. In all number systems with positional notation, leftmost digit in a number is most significant. It means it has highest place value, and rightmost is least significant. Lowest value or power of base is 0. For example, in number 729, most significant digit is 7 and least significant digit is 9. Decimal number system is a standard number system for humans. A decimal number system uses 10 as the base. The figures used are 0 to 9. Digits are multiplied with the powers of 10 according to their place value. For example, number 3239 can be expressed as 3000 plus 2000 plus 30 plus 9. And if we write it as in form of base, it will be 3 into 10 power 3 plus 2 into 10 square plus 3 into 10 power 1 and plus 9 into 10 power 0. One thing you should note that 10 power 0 is equal to 1. Powers of 10 start from right to left in decimal number. Number system that computers use commonly is binary number system. Binary number system uses 2 as the base. Figures used in this number system are 0 and 1. It is used in computers to represent the state of low volt or high volt. A specific combination of 0 and 1 can represent text, images, video, or audio in computers. Place value of digits in this number system is determined by powers of 2. Hexadecimal number systems uses 16 as base. First, 10 figures are same as decimal and 6 figures are taken from alphabet letters. This number system is also used in computers. One hexadecimal digit can represent 4 binary numbers. That's why this number system is used in assembly languages to represent strings of zeros and ones from machine language. Digits in this number system are multiplied by powers of 16 to convert to decimal number system. And the last number system we will learn about is octal number system. Octal number system uses 8 as the base. Figures in this number system are 0, 1, 2, 3, 4, 5, 6, and 7. This number system was also used in some earlier computers. One octal number could represent 3 binary digits. Digits in this number system are multiplied by powers of 8 to convert into equivalent decimal number system. This table represents equivalent of decimal, hexadecimal, and octal in binary number system. Any number system whose base is some exponent of 2 can be directly converted to binary. In binary, fourth digit place value is 2 power 4, which is equal to 16. And 16 is base of hexadecimal number system. Hence, each digit of hexadecimal in binary can be represented with 4 binary bits. For example, in number 3AF, 3 can be represented with 0011. A is 1010 or 1010 and F is 4 times 1. So the number will be 00111010 4 times 1, or we can drop leftmost 2 zeros and number is 000010 4 times 0 1. Octal has same kind of relationship with binary number system too, because 8 is 2 power 3. Each digit of octal number system is equal to 3 digits of binary number system. For example, in number 123, 1 can be represented with 001. In binary, 2 is 010 and 3 is 011. So the number will be 00101 0011. We can drop leftmost 2 zeros and the number will be 101 00 and 11. You have learned counting as a child. When you count higher than 9, you start using same figures to represent a number. Any number with figures 0 to 9 is a decimal number. Any number with figures 0 to 7 is a valid octal number. In octal, adding 1 to 7 will result in 10 because there is no figure of 8. In hexadecimal, adding 1 to F will result in 10, which is equal to 16 because there is no figure for 16. There is, however, positional notation. This is how positional notation work. Whenever value exceeds the number of base of number system, digits are shifted to next position to write a next number. It is assumed that you are familiar with arithmetic in decimal number system. Since the hexadecimal and octal number system are not very common in computers, there will be less reference to them in coming lectures. Following points must be noted whenever solving problems with number systems. The first point you need to take in account is when sum of digits is greater than the base of number system. For example, 7 plus 1 in octal is 10, 1 plus 1 in binary is 10, or 9 plus 1 in hexadecimal is 10. Second thing is that numbers are equivalent. 127 in octal number system is same as 87 hours in decimal number system. While performing addition in number system, following points must be noted: that 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 10. And doing subtraction, 0 minus 0 is 0, 0 minus 1 is 1 because 1 will be borrowed from digit left of the 0. 1 minus 0 is 1, 1 minus 1 is 0. I am assuming that you are familiar with borrow and carry in arithmetic. So you can understand the problem at right side of this slide. And if you are familiar with rules of arithmetic, you can also understand addition and subtraction in octal number system on this slide. Learning to convert from one number system to another is necessary to understand processing of information in a computer. Decimal number system is a standard number system for us. That's why all other number systems are created relative to decimal number system. Converting from decimal to other number system, number is divided with base of the new number system. Converting from other number system to decimal, digits of number are multiplied with specific powers of base and products are added. In algorithmic form, conversion can be described as while the quotient is not 0, divide the decimal number by the new base. Make the remainder next digit to the left in answer. Replace the decimal number with quotient. Converting decimal number 62 into binary number. Divide given number by 2 and keep the remainder. Divide the quotient recursively until it is 1. Keep each new remainder to the left of the current one. Or you can write binary numbers from bottom to top from remainders, first digit from left being the last quotient. Most significant bit will be the last quotient and least significant bit will be the first remainder. Converting from decimal to hexadecimal follows the same algorithm. That is, number is divided by 16 and the remainders greater than 9 are represented with alphabet letters. And same algorithm can be used in decimal to octal. That is, divide number and subsequent quotients by 8 and keep the remainder to the left of the current one. Here, number 231 is converted to all three number systems for your practice. Converting from binary to decimal, multiply each digit with powers of 2. Least significant bit or rightmost bit is multiplied with 2 power 0. Powers of 2 increase by 1 from right to left. Powers of 2 with most significant bit is 1 less than the number of binary digits in the number. Earlier we discussed polynomial form. You can convert a binary number to decimal using polynomial method too. Converting from other number systems to decimal follows the same process, just multiply with powers of base in a given number system. You can perform direct hexadecimal to binary conversion and vice versa. Replace each digit of hexadecimal with 4 equivalent binary digits. Starting from right, equivalent of f is 4 times 1, a is 1010 and 3 is 0011. And for binary to hexadecimal, underline digits in groups of 4 from right side. Converting from octal to binary and binary to octal follows the same process, only a number in octal is represented with 3 digits in binary. Everything is explained on this slide. I am leaving this slide for you to read. Thanks for watching this lecture. You can subscribe to my channel for more videos and for your appreciation.